Unit 2 is two-dimensional kinematics, meaning objects are going to move, again, in not just one dimension, such as the x, but also the x and the y direction or components at the same time. So it's a little bit different than Unit 1, where everything was moving either horizontally or vertically as we did some of the problems. We're going to need to use some of that information and use that understanding of that as we go into two-dimensional kinematics. So everything that we talked about in Unit 1 is going to be very important. Everything that we talked about in Unit 1, 0 and 0.5 are also important to have talked about. So all the vector stuff is going to come back and work with us. Now, why do we want to use vectors? Because it's going to make our lives easier than having to use calculus. Some of you that use calculus, it might be that it might work for you, but we're going to use algebra, and I believe it works out pretty nice when that happens. So the big difference between last unit and this unit is we're actually kind of combining things that were happening. Instead of just a car driving down the road, the car might be driving down the road and shooting something out of the sunroof and seeing what happens from there. So to kind of see where we're at on this, from the same height and the same time, one ball is dropped and another is fired horizontally. Which one will hit the ground first? Take a time, think about it. So the object that is both hit at the same time. So neither the dropped or the fired land first. They both hit at the same time. Now, why is that? Well, if you have an object launched from a certain height, and regardless of what the height is, if the object is launched outward and another object identical is dropped, they both hit the ground at the same time. Now, here's the thing. A lot of us think that the ball being dropped is going to hit first. Well, the ball being dropped and the ball being fired are both of them are affected by this something at the same rate, and that is gravity. Gravity is still affecting both objects equally. They both fall at the same rate, meaning they both will hit the ground at the same time. Now to follow up, by the way, now you have to answer both of them. In the previous problem, which ball had a greater velocity at the ground level? Which ball had the greater velocity at the ground level? The object that has a higher velocity at the ground level is the fired ball. You might have a greater net velocity. They both hit the ground at the same time. What bothers a lot of people on this one is because the fired ball, because even though they're fired from the same height in both cases, okay, they're both fired and dropped from the same height, because one goes horizontal and one just goes up and down, a lot of people want to say that the one that's going horizontal is going to stay in the air, but gravity is going to pull it down at the same rate. It hits the ground at the same time the other ball does, it just hits it out way farther away from you. Okay? There's a displacement horizontally that leads us to a misconception that they don't hit the ball at the same time. And it's that fact that the horizontally fired ball, because it has that great velocity horizontally, makes us think that it's not dropping at the same rate the other one is. But it is. Gravity's affecting it at the same rate. And this can be said no matter if you dropped two objects on a different planet. Their gravity is going to be affecting it the same way. It's going to hit the ground. So, we've already considered relative speed in one dimension. That's that most of the time we have been dealing with distance in the x direction, and therefore velocity in the x direction. Okay. We've also taken into account velocity in the y direction for objects that have heights. But now see, height can also be written as displacement in the y direction. Now, sometimes we're going to still be asked to add them as together. However, there will be still times that the velocity might change at different points. We know when it falls that it's also going to have a change in velocity because gravity is going to be there. And so in some cases, we still have to solve for the x component as well as the y component. Sometimes we have to solve them separately and then bring them together. And when we bring them together, we find that it makes a triangle that we have. And a lot of times, and especially for some of these, they're going to be right triangles. There are going to be times where they're not right triangles, but that's usually kind of the river example or some of the other ones that might have that happen. But a lot of times what we're going to be looking at are right triangles, especially for objects when they're launched or if they're falling off, say, a cliff, or if they're launched in the air, depending on what's happening. Okay? So we can't forget how to solve for those horizontal or vertical components, adding and subtracting them based on their vectors as we need to. But now we're going to take them and combine them together. So how we label these components or these vectors is also going to be an important part. Because, as you can probably guess, things can get very complicated very quickly. And so making sure that we're talking about the velocity of the boat to the water, the velocity of the boat to the shore, the velocity of the water to the shore. That's usually how they kind of go with it, is what to what. is what we'll look at is trying to get that as much as possible of what, so that we have and can solve for those parts. And this is a pretty common part, and you might actually see some of the problems that we have covered in vectors. Now we're bringing them back into the mix again and solving for them now based on our understanding of the science part of it as well. And so it's not going to be just, all right, here we go, solve for the equation based on the triangle that you have, but you're also going to be looking at the kind of the science, and does that make sense, especially when things are being launched. The ones such as the water, those are pretty common ones that a lot of times you don't need a good understanding of the velocity and that, but instead you have the ability to kind of go with the other and just start understanding this velocity and the other part of it as well. The components of a motion can be figured into the x and or y part of it, and so your distance can be the times the cosine of theta, so your theta would be whatever the degree is, and they are treated in the same way. They're just independent, such as your x and your y's can be there, your sine and cosine parts of it. So these two equations will help us and add some things to it as well. We should be able to also utilize these two equations, that it might not always be, say, distance, and that sometimes these could also be, say, it could be the velocity as well, depending on what we're looking at, and then therefore this would be the velocity of the directional component, such as x or y, and then it would be the, in some reference materials will say it is velocity of 0 or not, but it also is talking about the initial velocity as well, and then you would just multiply it by the trigonometric function, either cosine or sine of that theta that we have there. And so it can be utilized in that manner. So the example that an eagle is perched on a tree above water, spots a fish near the surface. It's going to go in for the kill. The eagle is able to maintain a constant speed of 3.1 meters per second at an angle of 20 degrees below the horizontal. How long does it take for the eagle to reach the water? That would be the time. How far has the eagle traveled in the horizontal? That would be, a lot of times you will see it as either your x or also written as d sub x. I've seen it written both ways in other reference materials. So I know it is sometimes frustrating in physics, like why can't they just have the same one? Well, I've also found that there are multiple times there will be like, oh, the label for density is a U or something. It's like, why can't we just all come to an agreement that everything has a certain label? Well, unfortunately, we can't do that with even our distance and or displacement, or in the with versus x versus d sub x. So whatever one it is, depends on the reference. So I'll resize this here so that I have some room to draw things out as best that I can. I think we're going to go simple on the drawings this time here. We'll just have some of the information that we need. Ruler here, and we have And we'll say that that is and see again, we have h, or that would also be written as distance in the y direction. And that would be 19.5. Let's go gray for my eagle. I'm just going to go a blob because pretty sure I'm not going to do a very good job on the other. We have a fish hanging out in some water. Maybe a little more cartoonish fish. With that, we know the velocity of the eagle is 3.1 meters per second, and that it is at a 20-degree angle below the horizontal, which kind of gives us that. To draw the triangle off to the side here, so it's the same triangle, but I'm just drawing it off to the side. We're going to draw this a little bit different, and let's use different colors of red here to kind of help us out. That would be velocity in the x. Go a little pink on that one. So velocity in the y direction. We'll keep that color the same for the 20 degrees. As well. And then I think we have, for the most part, let's put gravity in there. So I'd like to, even though it might not be technically needed, I like to have it in there just because. Because you never know, and I think it's a good reminder that what we need. And so what I'm going to do is I'm going to solve for the equations. We're going to solve for velocity in the x and the velocity in the y, utilizing the equations that we have, or utilizing our understanding of trigonomic functions, that the opposite would be give me the velocity in the y. So the sine of 20 times 3.1 would give me 1.06. Now, because of the way it's raw, because it's below the horizontal, and this is where I think some things didn't work out mathematically last time, 1.06, negative because it's below the horizontal. And now for then we would use the cosine of 20 times 3.1. And that is 2.91 meters per second. So we have a little bit more information for that. So now if we utilize the fact that we have a height and we have a velocity, we should be able to now, and gravity, we should be able to find that time a little bit better. Going from the top to the bottom, what will happen to the displacement? In this case, the displacement would be going, you'd almost be going negative because you're at the top and you're falling, right? And so, because of that, you can utilize the fact that you're up here, and as you go down, as the eagle goes down, it's 19.5 from the bottom. Now, if it starts at the top and goes down at 19.5, technically, a negative, it will travel a negative, write that a little bit better, it's going to actually travel a negative 19.5 meters. And then we can divide that by that. We then have a negative 1.06 meters per second. Now the signs are going to work themselves out, multiplying and algebraically manipulating this. Multiply both sides by t. Those cancel out. Utilizing then that we have the equation is t is equal to, yes, we'll go around it. We'll go to the algebraic. So multiply that by a negative 1.06 meters per second is equal to now a negative 19.5. This should be a 5. That written very well. 0.5 meters. Now then gives us, solve for t, divide both sides by 1.06 meters per second. To give us a time of 18.4 seconds.
How did you get the negative 1?
And now that we know that we have a time, and this time, regardless, time, because it's scalar, doesn't have a directional component to it, we can now use it to solve for the distance in the horizontal, kind of that part there, how far away, and you can go with the distance, and the x is equal to velocity times time, and we'll just say the velocity and the x, which is in some people's mind the preferred equation for distance or a velocity. So velocity is equal to distance is equal to velocity times time. I utilize the 2.91 meters per second that I had solved for earlier when solving for the equation. multiplying that by the time that I just solved for, to now give us the displacement in the x direction, and that is going to be 53.5 meters. In all, technically, the only thing different from this example than ones that we've been dealing with in the previous unit is the fact that we solved for a triangle earlier on. That's pretty much the only difference. All the other stuff, so to speak, is stuff that we learned in 1D. We're just applying it in 2 dimensions separately to solve for what we need.